So in today's lecture, we're going to continue where we left off in the last lecture. So we ended by talking about Max Planck and his mathematical model to explain black body radiation, in that the energy of a photon is equivalent to Planck's constant times the frequency of light of that photon. But recall that he came up with this mathematical model based on data, but did not necessarily believe his conclusion. Albert Einstein also made some statements about photons, in that photons are massless, but they have momentum. And we're going to learn today about how he determined that they had momentum, but did not have mass. There was another way of calculating momentum, since we know that momentum is mass times velocity. The momentum of a photon is equivalent to h, Planck's constant, divided by the wavelength. In the early 1900s, around this time, there was a lot of research going into light as a wave, and one of the scientists was Heinrich Hertz. And you might recognize Hertz. Remember, that is the unit for frequency. It's named after him. And he noticed that as you shined UV light at some metals, they would spark, which he called the photoelectric effect. So an apparatus like the one you see here has been set up, or was designed, in order to study this spark and to measure what that was, and to explain the photoelectric effect. And the apparatus is made up of a variable light source, and it's variable in two different ways. It has a variable wavelength that it can emit, but it also has a variable intensity, so how bright the light is. So the light is emitted from the source, and it hits this emitter, okay, which then will allow electrons to jump off of it and be collected by the collector. If the electrons jump off of that emitter, it creates a current in this circuit, okay, which the current, which is called the photocurrent because it is created by light, can be measured by this ammeter here. Now over here you'll see this, which should be unfamiliar to you. We've never looked at anything like this. This is a variable voltage source, which essentially means that you can change the voltage, adjust the voltage to whatever you want. Okay, and then here a voltmeter that then measures that. Okay, so in this type of experiment, you have two independent variables. There's light intensity, okay, which is controlled by the source, and light frequency. The dependent variables are the photocurrent, so the amount of current that is created, but also more importantly, and what we're going to look specifically at, is the stopping voltage. So essentially what this variable voltage source does here is, when a current starts to run through the circuit as a result of the electrons jumping up, we set up a voltage source that's going to oppose that current until it stops, which is why it's called the stopping voltage. Okay, and the stopping voltage, we know, which is this Vs here, is equivalent to the maximum kinetic energy of the electrons that are being emitted off of this surface. Okay, so let's look a little bit more into detail. I'm going to use a simulation to kind of show you how both light intensity and light frequency affect the stopping voltage and what that says about light itself. Okay, so if we take a look here, here's our variable voltage source, so I can adjust it. And here's our ammeter, it tells you the current. And then the variable light source, and I have a way of adjusting the wavelength, but also a way of adjusting the intensity here. So it's going to shine light on this emitter here, which is then going to allow electrons to jump off of it and be collected by the collector on this side. And if you look on the right hand side, we're using sodium, okay, so, and I could adjust and pick like different kind of metals, but we'll stick with sodium for now. So as I increase the intensity, I'm going to turn it up to like 50%. You can see that electrons start to jump off of the emitter and be collected by the collector, and I have a current here, okay? So what I'm going to do is I'm going to determine what the stopping voltage is. So all I do is I turn the battery on, and I just adjust it until the current is 0. And since I've already done this before and taken the time, I know that it's about negative 0.8 volts, okay, where it first starts to get at 0, okay. Now, if you notice, if I increase the intensity, let's say I increase the intensity to like 70 or 80%, If I'm still at 0, so if I adjust this voltage and turn it up, I'm still at 0. If I turn it down, the current starts to kick in. So the intensity does not affect the stopping voltage, okay, which is one of our first conclusions about the photoelectric effect. The light intensity has no effect on the stopping voltage. Okay, if we look back at our equation here, okay, we can see that the stopping voltage is equivalent to the maximum kinetic energy. So if I look, move my thing here. If we look back at the simulation, we can see that in this case my stopping voltage is 0.8 volts, which means that the maximum kinetic energy that my electrons have is actually 0.8 electron volts. So it's directly equivalent to the amount of electron volts, which, remember, is a unit of energy. Now, the reason why in this equation you have the E here is that is the magnitude of the charge of an electron, which is the conversion factor that we use to convert to joules. So if we were to plug in the charge here, then we would actually get the kinetic energy in joules. Okay, so now let's look at how the frequency affects the current and the stopping voltage. Okay, so I'm going to set it back to 0 for now. Okay, and you can see, well, just type it in here. I'm going to turn the intensity all the way up because I know it's not going to affect anything, okay? And now if I turn the wavelength down to like 250, okay? So remember that wavelength is inversely proportional to frequency. If you have a very small wavelength, that means you have a very high frequency. And really what we want to look at is frequency to stopping voltage. Okay, so when I turn it to about 250 nanometers here, you can see that the electrons are really excited and have a lot of kinetic energy, and I'm getting a pretty strong current. So I'm going to add some voltage until I get that to stop. Okay, and then I would repeat this with increasing increments and see how does that affect the stopping voltage. Okay, and then plot them in a graph. So I've already done this, so let's just look at the Excel document that I've created. Okay, so over here you can see I went between 150 and 530 nanometers, okay, and recorded the stopping voltages in this column, okay. But because I said I wanted to compare frequency to stopping voltage, here I had to convert from wavelength to frequency, and I just use the wave equation to do that. So if you notice here, that's 3 times 10 to the 8th divided by this number times 10 to the negative 9th. So that's taking the speed of light and then dividing by the wavelength in nanometers, okay, to get these frequencies. And I've plotted them on the graph, and even though you can't see the axis here, right here is stopping voltage, and right here is the frequency. So what you notice is that there's some point where there is a minimum frequency that is required for electrons to jump off and for a current to happen. So if we look, let's just turn this up to about 530, which is where it about is. Let me just type it in here. Okay. We can see that if we set the voltage to 0 at this position, at 530 nanometers, then the current is 0, okay? So there is a minimum frequency. It's called either the threshold frequency or the cutoff frequency that is required in order to allow electrons to jump off of a surface and therefore be collected by the collector and form a current, okay? So let's look at this graph in a little bit different way. Okay, if we look here, you can see in this graph that kinetic energy, the maximum kinetic energy of the electrons, is plotted versus frequency. But recall from that equation that we have, you can see it's still over here, that the stopping voltage and the maximum kinetic energy are equivalent. So the x-intercept is the point, the frequency that is the cutoff frequency, the minimum frequency, in order for photons to jump off of the surface of that metal. Okay, so how does Einstein explain this? Okay, so he said that a photon was a particle of light, okay, and it strikes a metal surface with an energy equivalent to Planck's constant times frequency. This is what Planck discovered. Okay, and since photons have momentum, They therefore encounter an electron. The electron absorbs the energy from the photon, and some of the energy goes towards releasing the electron from the metal, and some of it is converted to the kinetic energy of the electron. Okay, so some of it is to pull that electron away from the metal, and then some of it is actually like the velocity that goes into the electron, how fast it comes off, or its kinetic energy, which is related directly to its kinetic energy. Okay, so every single metal is a little bit different. If you look at this table here, you can see that there's a list of a bunch of different metals, which is why there's more than one metal in the simulation. Okay, and each metal requires a different minimum energy to release those electrons, which is related to the frequency. We just found, looking at the simulation, that there was such thing as that cutoff frequency. Okay. Now, it makes sense that different metals have different work functions. If you just think of their electron arrangement like you learned about in chemistry, it would make sense that some electrons would move off of an element easier than others. Okay. So the minimum energy required for a electron to jump off is called the work function, which is given by this variable here. Okay. So it would make sense that if the total energy of the photon is then converted into the work function, the energy to remove the electron, and the kinetic energy of the electron, that we have this equation here, where the energy of the photon is hf minus the work function gives us the maximum kinetic energy. Okay. Now, another cool thing is, if you see, this looks like the equation for a graph, right? So h would be the slope of my line. So this is the same as I saw before, maximum kinetic energy here, and then frequency here. This is y equals mx plus b. Okay, so b, remember, is the y-intercept. So if I were to extend my line below the x-axis, where it would hit the y-axis, or the y-intercept, is actually the work function for that metal. Okay, so let's just look at an example problem, okay, and how this could be related. All right, and let me make this bigger just so you can see it a little bit better. Okay, so here it says that you have a sodium surface, just like we were looking at in the simulation, and it's illuminated with a light of 0.3 micrometers. The work function for sodium is 2.46 electron volts, so that's that y-intercept. Find the maximum kinetic energy of the ejected photoelectrons, and B, the cutoff wavelength for the sodium. Okay, so the maximum kinetic energy for the ejected photons. So we need to use that relationship of the energy to our energy of the photon to the energy of the electrons we just looked at. Okay, so we have that energy of the photon striking is equal to h times f. And since we're given the wavelength of the light that illuminates the sodium instead of the frequency, we have to make that adjustment, right? So we take h and then we take c over the wavelength to sub in for frequency, okay? And then we just plug and chug, and depending on what Planck's constant we use, it determines what unit that we end up with. So we end up with 6.63 times 10 to the negative 19th joules, or 4.14 electron volts. Okay, so now we want to know actually the kinetic energy of the electrons. So we would take that kinetic energy max, take the h times f minus the work function. So we have our h times f, that's what we figured out up here. So in this case, we use electron volts, 4.14 electron volts, minus the work function, which is 2.46 electron volts. So we use electron volts here just because our work function was given to us in electron volts, but we can easily convert back and forth, okay? So we get that the maximum kinetic energy is 1.68 electron volts, okay? Now, the second part of the question asks us the cutoff wavelength and how that can be calculated, okay? So in order to do the cutoff wavelength, it's important that we convert back to joules. We have our kinetic energy in joules, okay? So the first step here shows taking the work function and putting the work function in joules, right? So the wavelength times the work function is equal to h times c. Okay, or h times c divided by the work function gives you the cutoff wavelength. So again, we just plug and chug our numbers. We've got our energy of the photon, or we have our Planck's constant, we have the speed of light, and then we divide